In the last few sections, we took a look at all different techniques for finding integrals. We did double integrals, we did triple integrals, we did them over rectangular regions, over non-regular regions, we did them over polarly defined regions, we did cylindrical coordinates and spherical coordinates. Well, now we're going to take all that information and apply it somewhere. So these are some integrals for mass calculations, mass density, and so forth. When you think about a center of mass, and you can look at some of the pictures that I have up in the PowerPoints, you're thinking of like holding a region on a pencil. Where should you put that pencil so that you can perfectly balance it? So we're going to look at centers of mass in 1 dimension, 2 dimensions, and 3 dimensions. Here comes that old rho again. So rho is going to be a density function that you can integrate on the interval from A to B. In 1 dimension, we're talking about things like a thin rod or wire. Center of mass is located at this point. Right? It's going to be the total moments, that's your capital M, and the mass is your lowercase m. So if you want the total moments, what you do is you take the integral of all the x times rho of x. And then your mass is the integral of all the rho of x's. Take them and divide them. You'll have the center of mass in 1 dimension. So let's take a look at this. We're talking about a thin wire or a thin rod. Here is our density function. So what does this mean? This means that as the object gets further along, it gets more dense. It's not a uniform density. So you can calculate this in a couple of different ways. Maybe I'll calculate the mass, the moments, and then we'll divide them at the end. So the mass is simply the integral of the density function. So integrate from 0 to 1 of 1 plus x to the third dx, and that gives me x plus x to the fourth over 4. If I put a 0 in, I get nothing. So really all I end up with is 1 plus a fourth. I'm going to turn this into an improper fraction, 5/4. So that's the mass. Great. Now I'd like the sum of what we call the moments. So the sum of the moments is the sum of all the x times p of x's. So again, same limits of integration. X times rho of x, so 1 plus x to the third. And that gives me the integral of x plus x to the fourth. Don't forget to multiply by the x first, then take the antiderivative. So that gives me an x squared over 2 plus x to the fifth over 5. Evaluate at 1 and at 0. So if I put a 0 in, I just get nothing. If I put a 1 in, I get a half plus a fifth. All right, in terms of a common denominator, that's 5/10, that's 2/10. So add them together, I get 7/10. Now, which way do I divide it? If I want the center of mass in 1 dimension, right, because we're only on a thin rod or a thin wire. So if I want to find out where that center of mass is, it's only going to be 1 coordinate. All right, so that center of mass is the capital M, which in this case is 7/10, divided by the mass, which is 5/4. Hey, if you want to multiply both sides, top and bottom, not both sides, by 4/5, I end up with a 28 on the top, 50 on the bottom. I can knock a 2 out of everything. 14 over 25. That's my center of mass. All right, so there it is for a 1-dimensional object. Easy calculation. Well, at least in 1 dimension. In 2 dimensions, now you're finding a mass per area. So instead of thinking about a thin rod and trying to find the center of mass of this little rod here, like in our case, it was a rod that went from 0 to 1, we wanted to find out where the center of mass was, so it was 14 over 25. Whereas 14 over 25 is a little bit more than halfway through, which makes sense because it's more dense as you go further to the right than the left. So if you want that seesaw to balance, the center of mass has to be past the halfway mark. All right, so now we've got a density function in 2 variables. So the center of mass is going to have both an x-coordinate and a y-coordinate. If the density of that plate is constant, then the center of mass is called a centroid because it only revolves around the shape of that plate if the density of the plate is a constant. In the process of giving an example, I'm also going to do a little bit of review here. This is a picture of how the formula is evolving. You've got now this thin plate instead of a rod, which means you're going to need 2 coordinates for your center of mass. It is sort of counterintuitive, but not really. The center, the x-coordinate, is going to be how far you are across this way. All right? So it's going to be the sum of the moments with respect to y divided by the mass. So these are all the distances from the y-axis. The ones over here are going to be distances from the x-axis. So the y-coordinate is going to depend on distance from the x-axis, and the x-coordinate is going to depend on distances from the y-axis. So when you take a look at the formula that comes out of it, now you're going to have two pieces. Looks similar to the one in one dimension, except now you're going to have to figure out which ones are the x's and which ones are the y's. So the first one, if you want the x-coordinate, you'll take 1 over the mass times the integral over the region. The other one will be the same thing, except you notice that when you want the center, the x-coordinate, you multiply x times the density. When you want the center for the y's, you multiply y by the density. All right, and it talks here about the centroid too. I obviously took this out of the textbook. I did not write it quite that fancy. All right. Let's take a look at this example. I want to find the mass and centroid of this plate. I'm assuming constant density, so it's a density of 1. That would make sense. For the region bounded by e to the x, e to the negative x equals 0, and x equals the natural log of 2. So what does this look like? E to the x comes up like this. E to the negative x comes down like that. No, it doesn't. It goes through 0, 1. So one comes up like this. The other comes down like that, right, asymptotic to the x-axis. And this will be the natural log of 2. So it's this region in here that we're talking about. Where do the y values go in that region? Well, the y values go from this bottom curve here, right? That bottom curve is e to the negative x, and it goes up to that top curve there, which is e to the x. So the y values go from e to the negative x to e to the x. Where do the x's go? Well, they go left to right. So they start at 0, and they end here at the natural log of 2. So the first thing is, let's find the mass. I'm going to start way up here because we're going to need the space on this one. So the mass is going to be a double integral. We said the density was 1. Let's integrate dy dx. Our y limits of integration were e to the negative x, e to the x. Our x limits of integration were 0, and the natural log of 2. So the inside one first will just give me top minus bottom. So it'll give me e to the x minus e to the negative x. Great. Now I get to integrate this from 0 to the natural log of 2 with respect to x. So the antiderivative of the first term will give me e to the x. Don't forget, when you take the antiderivative of the second term, it pops out that extra negative 1, so you end up with plus e to the negative x. Evaluated at the natural log of 2 and at 0. So this gives me e to the natural log of 2 plus e to the negative x. Isn't that just 1 over e to the x? So maybe it'll make it easier if I write this as 1 over e to the natural log of 2. So that's the upper limit of integration. Don't forget there's a lower limit of integration. E to the 0 plus 1 over e to the 0. Now let's simplify. Remember the rule, e to the natural log of a number is just that number. So I get 2 plus 1/2 minus e to the 0 is 1. 1 over e to the 0 is also 1. So I end up with 2 plus 1/2. This should be a minus, right? Distribute the negative sign, so I got a minus and a minus. So 2 minus 2 is 0. That's a 2. That's a minus 2. And it turns out my mass is just 1/2. So hang on to that number because you're going to need it in both calculations. All right. Now we've got to do 2 other calculations. Let's do the y one first, the y center, because that's actually a shorter calculation. The center for the y is going to be 1 over the mass times a double integral of y times rho of xy integrated over the area of the base. So what is that? Well, if the mass is a half, 1 over a half is just 2. So my midpoint here is going to be 2. We said the density was 1, so I'll get y times 1. And then let's do dy dx. More complicated one first. So e to the negative x is the lower limit. E to the x is the upper limit. For the x's, I go from 0 to the natural log of 2. All right. So that will give me, if I take the antiderivative of the y dy, I'll get y squared over 2, and then evaluate it at e to the x, e to the negative x. So that'll give me e to the 2x minus e to the negative 2x all over 2. Now, check this out. There's a 2 out here on the top. There's a 2 down there on the bottom. Cancel them out. So now I'm going to integrate from 0 to the natural log of 2 of e to the 2x minus e to the negative 2x, this time with respect to x. Right, so that'll give me an e to the 2x over 2 plus e to the negative 2x over 2. Now do your substitution. Evaluate it at the natural log of 2. And this will give me e to the 2 natural log of 2 over 2 plus e to the negative 2 ln 2 over 2 minus e to the 0 over 2 minus e to the 0 over 2. Right? Normally it would be a plus, but I'm distributing my negative right away. All right, how do I evaluate this? That 2 can come up to the top, make it 2 squared, and that's how I end up with a 4. So e to the natural log of 4 is just 4. So I get 4 over 2. If this thing comes up to the top, what do I end up with? I end up with a 2 to the negative 2. 2 to the negative 2 is 1/4. So that e on the top becomes a 1/4 divided by 2. E to the 0 is 1. E to the 0 is 1. All right, this will be a relatively nice number. 4 divided by 2 is 2. Quarter divided by 2 is an eighth. And then minus 1. So 1 plus an eighth, 9/8. That's my y center. Okay, hang on to that number too. All right, what if I want to find the center for the x? Well, now I need to do the same thing, except I need to multiply by x when I do my calculation. So the center of mass, the x-coordinate, will still be 1 over the mass times the double integral, this time of x times rho of xy, integrated over the area. So 1 over 1/2 is still 2. Double integral of x times 1 dy dx, same limits of integration. Right, and when we get an answer to this, then we'll be done. We just have to put them together into an ordered pair. 0 for the lower limit, natural log of 2 for the upper limit. All right, this will be a little funky. When I integrate this with respect to y, I get xy. Evaluated at y equals e to the x and y equals e to the negative x. This is going to cause me perhaps a little heartburn because I'm going to end up with the integral from 0 to the natural log of 2, carry down the 2 that you had before, of x times e to the x minus x times e to the negative x. How do I do that? Integration by parts. And one of the reasons I picked this problem is I want to do a review of integration by parts in case you haven't seen it in a while. I'm going to do one of them by integration by parts, and then I will let you work the other one out and combine them and everything, and I'll tell you what I got for an answer at the end. So suppose I want to integrate x e to the x. All right, so I want to integrate x e to the x with respect to x. I need to pick a u and I need to pick a dv. The other two pieces will come from whatever I choose. So my du will go over here, my v will go over there. You want to pick a u that derives easily and a dv that integrates easily. So for my u, I'll choose x because you can't get much easier than that to derive. For the dv, I'll end up with an e to the x dx. And I want to pick a u, if I can, that will derive itself away, right? If I choose u to be e to the x, it's just going to keep going. All right, the derivative of x is just 1 dx. The antiderivative of e to the x is e to the x. Right, if you remember the formula, you're going to get uv minus the integral of v du. So uv goes right across from each other, x e to the x, minus the integral of e to the x dx. All right, that'll give me x e to the x minus e to the x. Now we need to evaluate that where? At 0 and at the natural log of 2. So I'll get ln 2 e to the ln 2 minus, do we realize e to the ln 2 is just 2? And then the bottom one will give me 0 minus e to the 0, which is 1. So e to the ln 2 is just 2. So I get 2 ln 2 minus 2 plus 1, which is 2 ln 2 minus 1. That's the first part. Then you got to do the second part. When you do the second part, just watch your signs. Here, let's do it because this is kind of fun. The second part is going to be the integral of x e to the negative x dx. Again, from 0 to the natural log of 2. I'll keep the pattern going. I'll pick u as x. That'll make my du dx. My dv will be e to the negative x dx, which will then make my v negative e to the negative x. So when I set up my formula, I'll get negative x e to the negative x, here's my uv, minus the integral of v, which is negative e to the negative x dx. I would combine my signs first. Negative x e to the negative x plus the integral of e to the negative x dx. And now when you take that derivative, you'll end up again with a negative because when you take the antiderivative, it pops out a negative. So you get negative e to the negative x and then evaluate. So at the natural log of 2 and at 0. So I end up with the negative natural log of 2. And then what is e to the negative natural log of 2? We did it up there, but let's do it again. E to the negative natural log of 2 is going to be the same thing as e to the natural log of 2 to the negative first, right? Because I can bring that up to the exponent spot. So that should give me a half, right? E 2 to the negative first is a half. So negative natural log of 2 minus a half, and then minus 0 minus 1, right? Because e to the negative 0 is 1. All right, so what does this give me? Negative natural log of 2 minus a half plus 1 is negative natural log of 2 plus a half. Now we got to combine our answers together. All right, my red answer up there is the end of the previous problem. And remember, it's that minus this. So it's got to be 2 ln 2 minus 1 minus negative ln 2 plus a half. So 2 ln 2 plus ln 2 minus 1 minus a half gives me 3 natural log of 2 minus 3 halves. Okay. somewhere at the very beginning of this whole problem, there was a constant. I swear there was a constant. And there it is. It's this 2 over here that's got to carry itself down. So when I come all the way back down here, I got to multiply this guy by 2. So I end up with 6 natural log of 2 minus 3. So what is my center? My x-coordinate is 6 ln 2 minus 3. My y-coordinate is 9/8, and that's the center of mass. We'll take a look at a couple of other density examples in the next video.